When talking about nuclear chemistry, it's important to understand where the elements of the periodic table came from. After all, nuclear transformation is the sole reason why we have different elements for the periodic table. And so, in order to understand how we developed our ability over nuclear reactions, we must first understand how they occur and where they occur. And so, we need to talk about the Big Bang. And if you know anything about the Big Bang, you might know that it was a TV show that was quite good, but that's not the Big Bang we're talking about. The Big Bang we're talking about is the one that was responsible for the universe formation. It was a singularity, that is, a single event which is responsible for everything in existence and the rules which govern them. And it's hard to say what happened in the first few seconds of the universe, but we know within the first couple of minutes, we had the particles which are responsible for making up protons, neutrons, and electrons. Protons and neutrons are the result of particles known as quarks. And quarks have different values which are beyond the scope of this class, but needless to say, protons and neutrons are made up of up and down quarks. Electrons come from different subatomic particles known as leptons. Again, well beyond the scope of this course, but it does give you an insight into what nuclear physicists think about. Well, what did we get from the Big Bang? Well, almost exclusively hydrogen. Hydrogen was the first and is to this day the most predominant element in the universe. Hydrogen comes in three forms. That is, there are three isotopes of hydrogen. The first one being hydrogen, which is just a single proton and an electron. We have deuterium, which was thought to be a different element for a long time before we could actually experimentally prove that deuterium was the same as hydrogen. Deuterium has a proton and a neutron along with an electron, and it has twice the mass of a hydrogen atom. Deuterium is stable, but it is in the universe in a very small abundance. Tritium is a third and final isotope of hydrogen and is radioactive. It's consistent of a proton and two neutrons. Tritium still exists today, and one of the major contributors to tritium on Earth is from the sun. Tritium has a half-life of somewhere around 20 years, so it is fairly short-lived in terms of radioactive materials, but it is also useful. Now, as we know, atoms are the smallest stable piece of matter that can exist. While quarks and leptons are smaller, they don't remain individual particles on their own. They combine to form our subatomic particles. Each atom is defined by the number of protons it has. And as we know from our study of the atom so far, we have our protons, neutrons, and electrons, which compose the atom. Well, after the universe spat forth all of this hydrogen gas, we had a very hot and dense but rapidly expanding universe. And as the universe continued to expand, the heat began to dissipate and the universe began to spread out. To give you some perspective of just how hot the universe was, we can say that the first 10,000 years of the universe was well above 20,000 Kelvin. In fact, at 300,000 years, we had dropped to 3,000 Kelvin. So an infinite amount of energy, or an infathomable amount of energy, is associated with the formation of the universe. So most of the universe was hydrogen. We had a little bit of helium present too, but that was really much it. The universe wasn't too exciting. You had hydrogen, which could react with other hydrogen atoms, so making H2 gas, and helium, which is completely inert. And for about the first 400 million years or so, we had really nothing occurring other than the expansion of the universe. So during this time, gases are expanding out into creation, and as gases begin to extend out, we notice that the nature of the galaxy of our universe is not spherical, but rather more elliptical. And because of that, there would be regions of gas that were higher in concentrations than other areas. And what happened was these gases began to condense back down into a region of space, forming a star or a planet. And it's these first generation of stars, which were all identical, that produced several of the elements of the periodic table. In fact, all first generation stars are responsible for creating the elements hydrogen through iron. They were all fairly identical. Now, inside the star, we have protons of hydrogen coming together, slamming together at tremendous velocities, causing a nuclear transformation, forming in either helium or lithium or beryllium. Here we have a diagram showing just a few combinations of nuclear reactions which produce the elements lithium and beryllium. You can see that there's up to 12 different steps that you can have to get to a stable isotope of lithium. And after a certain amount of time, these first generation stars had spent their energy and they would end up going nova. So they would spill their contents out into the surrounding universe, and they would be allowed to expand out into space. And these newly formed elements would then again begin to congregate, except this time we're starting to develop our second generation of stars. We now have more than 2 elements in the universe, and so the composition of our second generation stars begins to vary, and vary quite significantly. We can have white dwarfs and red giants in addition to our regular stars. And the nuclear reactions that occur within these stars is quite different. After all, we got iron through the first generation of star, but it's really the result of the giants that produce all elements beyond iron. They're the only ones that are big enough that have the pressure and temperature needed to continue to force protons and neutrons together beyond what they're most comfortable at in terms of stability. And so what happens is we have a star go supernova, it kicks out most of the elements beyond iron, and then the star collapses on itself to make a black hole. So at some point, the contents of you, of me, of the earth, of your computer, of everything has been in a star. Something rather quite remarkable to think about.